This video discusses the differentiation of the natural exponential function. What is natural exponential function? The natural exponential function is e raised to the x. I hope you still remember the natural exponential function e raised to the x from college algebra. So today we will see how to differentiate e to the x. Not only e to the x, but also we will look at how to differentiate composite functions of the natural exponential function. But first we need to look at the differentiation of e raised to the x. We can look at this problem by first looking at the graphs of exponential functions. How would you draw the graph of y equals a raised to the x? Let's say for a greater than 1. When a is greater than 1, the graph of an exponential function y equals a raised to the x will be like the one I'm going to show you now. Let's assume that these are our x and y axis. The origin is right here, and the exponential function should be something like this. What is this coordinate point right here? The x coordinate is equal to 0, and at that point the y coordinate should be equal to a raised to the 0th power. Any number raised to the 0th power is equal to 1. Therefore, the coordinates at this point are 0, 1. Therefore, let me label that y coordinate at that point as 1. Now, if I have to draw another exponential function, let's say y equals b raised to the x. If that b is larger than a, it will be below the green curve for all the negative values of x, and it will be above the green curve for all the positive values of x. Likewise, if you have to draw another exponential function such as y equals c raised to the x, and if that c is less than a, remember still that c should also be larger than 1. However, if that c is smaller than a, it will have a graph which is above the green line for all the negative values of x and below the green line for all the positive values of x. I just wanted to mention those things because I need to pay attention on one specific point. That specific point is the point 0, 1. At that point, if I would like to draw a tangent, what will be the equation of that tangent? Well, of course, in order to find the equation of the tangent, I should know the slope. Slope is, let's say this angle is theta. Well, of course, I already know the coordinate point right here, which is 0, 1. So if I already know the angle theta, I can find tangent theta. Using those two pieces of information, I can write down the equation of that red straight line, which is the tangent drawn to the green curve at 0, 1. You can see when you have multiple exponential functions, their tangents drawn to the curves at 0, 1 will have so many different values of theta. However, is there an exponential function, just one exponential function, so that the slope drawn to the curve at 0, 1 at this point is going to be equal to 1. The slope is equal to 1 means that angle theta should be equal to 45 degrees. Is there an exponential function meeting that requirement? Well, there is just one exponential function meeting that requirement. That exponential function is e raised to the x. In fact, that exponential function will have infinite number of derivatives, and for all of those derivatives, if you look at the slope at 0, 1, they are all going to be equal to 1. Can you write down an equation satisfying that condition? Not only all of those derivatives, but also the value of the function when x is equal to 0 should be equal to 1. Can you write down a function to meet all of those conditions? Let's say I'm going to write down a function like this. At x is equal to 0, the value of that function should be equal to 1. Alright, right here. You differentiate it one time, still the value of the function at x equals 0 should be equal to 1. I can easily do it by adding an x, because if you differentiate it once, the 1 right here will be gone and this x will become a 1. Now I need that function still to produce 1 even if you go for the second derivative. Of course, with the second derivative, the 1 is gone and x is also gone, and for the second derivative, I will consider something like x squared. if I go for the second derivative, this is equal to 0, this is also equal to 0, but the second derivative of the x squared term, the first derivative is equal to 2x, you differentiate it one more time, you get a 2. So the second derivative will be equal to 1 if I had this number divided by 2. And I also need the third derivative of this function to be equal to 1 when x is equal to 0. If I go up to the third derivative, all of these three existing terms will be equal to 0. So for the third derivative, I will need an x raised to the third power. So if I differentiate x cubed once, I will get 3x squared. And if I differentiate that term one more time, it will be 3 times 2x. And if I differentiate that also one more time, it will be 3 times 2 times 1. So if I divide this quantity by this value right here, 3 times 2 times 1, then the third derivative of all of this should be equal to 1. Therefore, let me go ahead and divide x cubed by 3 times 2 times 1, which I will write as 3 exclamation mark. In fact, this is read as factorial 3. Now, we will do it one more time. Let's say I would like to differentiate that function for the fourth time, and I need even the fourth derivative evaluated at x equals 0 to be equal to 1. So, if I go up to the fourth derivative, this term is going to be 0, this is also going to be 0, this is also going to be 0, even this term is going to be 0. So, at the fourth derivative, I will need a non-zero term which will eventually be x raised to the fourth power. That will also have to be divided by something so that this function is equal to 1 at the fourth derivative. So, x to the fourth, if you differentiate it one time, you get 4x cubed. You differentiate it one more time, since 4 is a constant, I can just take it out. That will be times 3x squared. You differentiate it for the third time, you get 4 times 3 times 2x. You differentiate it one more time, you get 4 times 3 times 2 times 1. This quantity I will write as factorial 4. So I need to divide this x to the fourth by factorial 4. Now this sequence should be clear to you. If I wanted even the fifth derivative to be equal to 1 when evaluated at x equals 0, the simplest term that should be added is x raised to the fifth power divided by factorial 5. Likewise, if I need all of those derivatives to be equal to 1 at x equals 0, the simplest function that I can write down will have infinite number of terms, and they will all look like this. This specific function was called the natural exponential function. We write it as e raised to the x. Now we are going to see what we will get if you differentiate this function. But before looking at that, we will also calculate the Euler's number, because this e is also called Euler's number. If I would like to calculate Euler's number, I can use a substitution x equals 1. When I use x equals 1, on the left hand side, I will have e raised to the first power. That should be equal to, on the right hand side, I get 1. Second term is just a 1 again. The third term is x squared over 2. When x is equal to 1, it's going to be 1 squared over 2. And the fourth term is 1 cubed, which is just 1 over factorial 3. And the fourth term is, once again, 1 raised to the fourth power divided by factorial 4. The fifth term will be 1 over factorial 5. And likewise, if I had written down the next term, it will be 1 over factorial 6, and so on. This will have infinite number of terms, and if you add all of those terms, you can find the exact value of the Euler's number. But nobody has found the exact value of Euler's number so far. We have good approximations for the Euler's number. So one simple exercise would be that you go ahead and use your calculator and add these numbers, and then find the value of e using that first set of numbers and compare it against the value that your calculator gives you as the value of e. If you use your calculator, you can see that the value of E is equal to 2.71828. In fact, if you look at the summation of these numbers written already, it'll be very close to 2.7. All right, now we will go on to the differentiation of the natural exponential function. In fact, this exponential function is called the natural exponential function because there are so many things that are available in the nature that can be modeled using the natural exponential function or the composite functions that are written down using the natural exponential function. So now we are going to look at how to differentiate the natural exponential function. How did we write down e to the x? We wrote down e to the x, the natural exponential function, as 1 plus x squared over 2 plus x cubed over factorial 3 plus x to the 4th power over factorial 4 plus x to the 5th power over factorial 5 plus x to the 6th power over factorial 6, and so on. There are few comments to be added. Remember, any number like, let's say, factorial 4. What's the meaning of that? It is 4 times, 3 times, 2 times 1. Let's say if you wanted factorial 5. Factorial 5 is equal to 5 times, 4 times, 3 times, 2 times 1. That part can also be written as factorial 4. Keep that in mind. In addition to that comment, I should also mention something else. 2 can also be written as factorial 2. So if I write down this also as factorial 2, it may be somewhat easier to remember. If you like, under x also you may write down divided by 1 factorial. In fact, under 1 also you may write down that divided by factorial 0. Because by convention, factorial 0 is accepted to be equal to 1. Maybe this form of this expansion could be easier for somebody to remember as the exponential function. All right, now we will go ahead and differentiate that function. I need to differentiate the natural exponential function with respect to x. Basically, I'm going to differentiate each of these terms on the right-hand side of the natural exponential function. When we do so, the first term becomes, it is a constant. When you differentiate it, it becomes just a 0. So I will not write that down. X over factorial 1. If you differentiate x, it's going to be just a 1. 1 over factorial 1. And then we have to look at this next term. Factorial 2 is in the denominator, which is a constant. Therefore, the derivative of that term is going to be 2x divided by factorial 2. The next term is x cubed over factorial 3. Differentiate it, you get 3x squared over factorial 3. Differentiate the next term, you get 4x cubed over factorial 4. Likewise, if you differentiate the next term, it will be 5x to the 4th over factorial 5, and so on. Now, we can do some further simplifications. Of course, 1 over 1, this first term is just equal to 1, and there's a plus sign. What can you say about this second term? It's 2x over factorial 2. The 2's can be cancelled, therefore it just simplifies to be equal to x. And there's this plus sign. And then how about this next term? On the numerator, I have 3 times x squared. On the denominator, I have factorial 3. And we saw earlier that this factorial 3 can be written as 3 times factorial 2. As soon as you write it that way, you can cancel off the 3 from the numerator and the denominator respectively. Then that second term simplifies to become x squared over factorial 2. Similarly, there is another plus sign, and the factorial 4 in this term right here can also be written as 4 times factorial 3. And then it can also be simplified as 4's are cancelled from the numerator and the denominator respectively. So that next term also becomes x cubed over factorial 3. You can see the same thing happening with the next term. That 5 in the denominator can be written as 5 times factorial 4, and then you can see that 5 from the numerator and the denominator can be divided out. Then that term becomes just x raised to the 4th power over factorial 4. Likewise, we can now identify this sequence. The next term should be x to the 5 over factorial 5, and so on. It continues with infinite number of terms. But what is this result once again equal to? That is the same definition of e raised to the x. Therefore, I'm going to go ahead and write this to be equal to just e raised to the x. This is a very powerful function in all of mathematics, because if you differentiate the natural exponential function, the answer is the natural exponential function itself. It has to be mathematically more completely said. If you differentiate e raised to the x with respect to x, your answer is e raised to the x. Please remember this result. This is an extremely important result in mathematics. There are so many applications of that. This is the only one function in all of mathematics where the first derivative is equal to the function itself. Because of that connection, not only the first derivative, also all the other higher order derivatives are going to be just equal to that same function. Alright, since this result is so very simple, we are not so interested in differentiating e raised to the x. Because if you differentiate that, you already know the answer. It is just e raised to the x. So what we practically need to know is how to differentiate e raised to a function of x. So now we will see how to differentiate e raised to a function f of x. We simply have to use the chain rule. In this case, I need to differentiate the function e raised to the f of x with respect to x. What is the chain rule? We can write it down as d by d f of x, this function, e raised to the f of x, and that times d f of x over dx. Please note that I didn't change the question given. On the left hand side, I have d e f of x over dx, and on the right hand side also, since these two terms can be cancelled out, we simply have d e f of x over dx. So I have not changed the question given. In fact, I have just applied the definition of the chain rule. So when you differentiate e raised to the f of x with respect to f of x, what should be your answer? It's like differentiation of e raised to the u with respect to u. That should be just equal to e raised to the u. We already proved it. In fact, when we proved that one, we didn't use a u, we used e to the x. But we said when you differentiate e to the x with respect to x, you get e to the x, the same function. Therefore, if you differentiate e to the f of x with respect to f of x, your answer for that part should be equal to just e to the f of x. Therefore, this is equal to e to the f of x. That's the first part only. And then I have this second part. This answer times the derivative of f of x with respect to x, which I will simply write as f prime x. This is the derivative of e to the f of x with respect to x. Please note that f prime x is the first derivative of f of x with respect to x. This is also a very important result. Please try to remember that. We will do a couple of examples. But before that, let me revisit this result real quick. If you have to differentiate e raised to the f of x with respect to x, the answer will be exact same e raised to the f of x that times simply differentiate the function in the exponent f of x. Once differentiated, it is going to be equal to f prime x. So we will do a couple of examples. Here's your example number 1. Differentiate y equals e raised to the 3x. What should be your dy by dx? The answer is this function itself times the derivative of the exponent. So it will be e raised to the 3x times the derivative of the exponent is just 3. In fact, you can write it more nicely as 3 times e raised to the 3x. That's the final answer for that problem. We will discuss another question. This is your example number 2. Differentiate with respect to x. Here's the function 3 times e raised to the 5 sine 2x. How about that? That should be equal to, what can you say about the 3 right here? It is just a constant. According to the second property of differentiation, I can factor that out. Once you factor that 3 out, I just have to differentiate with respect to x the function e raised to the 5 sine 2x. How do you differentiate that? This is going to be equal to, let me write down the 3 right here. First of all, 3 times the differentiation of all of this part. When you differentiate that part, I need to simply write down this function as it is. That is the first part of that differentiation. When I do so, it will be e times 5 sine 2x, and then I need to differentiate this exponent. 5 times sine 2x should be differentiated. When you differentiate that, we know the answer is going to be 5 times cosine 2x times 2. We will simplify that, then you get 3 times 5 is 15 times 2 is 30. 30 times e raised to the 5 sine 2x times cosine 2x. That's the final answer for that problem. All right, we will look at another example. Here's your example number 3. This time we will differentiate the function given as y equals x squared e to the 5x minus 3. When you find dy by dx, how would you differentiate this first part? Please note that it's a product of 2 functions of x, which means you need to use the product rule. So what is the product rule again? If you have a product of 2 functions f times g to be differentiated, it's going to be equal to f prime g plus f g prime. Now if I label x squared as the function f and e to the 5x as the function g, I know f prime is going to be equal to just 2x that times g as it is, which is e to the 5x, plus f times g prime. F is x squared times g prime. E to the 5x derivative is equal to e to the 5x times a 5. Please do not forget to differentiate the exponent. All right, and then if you differentiate the 3 right here, it's going to be equal to 0. Therefore, we have already completed the differentiation, but we can keep the answer a bit more nicely by simplifying it a little bit more. I can factor out an x, I can factor out e to the 5x as well. Open parenthesis, from the first term I will have a 2 and plus 5x, close a parenthesis. That's your final answer for this problem. We will look at one more example and we will call the day. Here is your example number 4. Let's say y is equal to 1 over square root 2 pi e raised to the negative x squared over 2. Have you seen this function before? This is a very popular function. This is called the standard normal distribution. This function can be easily differentiated. What cannot be done with this function is actually the integration. Of course, in this section, we are not going to talk anything about the integrations. We will simply differentiate this function. We will find dy by dx. Dy by dx should be equal to, what can we say about 1 over square root 2 pi? It's a constant. Therefore, I can simply write that as it is, 1 over square root 2 pi. I simply have to differentiate this function, e raised to the negative x squared over 2. First, we will write down that function as it is without any changes whatsoever, e raised to the negative x squared over 2. That times the derivative of the exponent. When you differentiate that exponent, we are going to get a negative 2x and there's a divided by 2 in the denominator. Now we can simplify this one a little bit. Then we get dy by dx to be equal to negative x over square root 2 pi times e raised to the negative x squared over 2. That's the final answer for this problem. I need to add a couple of comments. The first comment is all the properties of differentiation should be equally applicable for any differentiation, including the differentiations involving the natural exponential function. So please make sure to apply all the properties correctly. That basically means if you see the natural exponential function is multiplied with another function, please don't forget to apply the product rule. And if you see a quotient, which may also involve the natural exponential function or a composite form of the natural exponential function, you must still use the quotient rule. Please do not forget those previously discussed properties where applicable. That's the first comment. The second comment is, please do not mix up the differentiation of exponential functions with the differentiation of x to the n. Because x to the n is not an exponential function. Why it is not an exponential function? Because this exponent right here is not x, it is not a function of x. Therefore, x to the n is not an exponential function. For x to the n, the derivative, if you differentiate this with respect to x, we know the answer is going to be equal to n times xn minus 1. Please do not apply this result whatsoever to differentiate any single exponential function. For example, I need to differentiate a number raised to the power x. You cannot differentiate this guy similar to the differentiation of x to the n. So just remember that to differentiate any exponential function, including the natural exponential function or any composite functions involving that natural exponential function, such as e raised to the f of x in general, we cannot use this result, differentiation of x to the n, whatsoever. If you ever use that result, your answer is guaranteed to be completely incorrect. Just keep those two comments in mind when you differentiate the functions involving the natural exponential functions. All right, let me stop the video at this point. Thank you so much.